Okay, good morning, everybody. Thank you for coming. I'm going to talk about compilation times. So first, a little bit about myself. My name is Vittorio Romeo. I've been working with C++ for around 10 years now, over 10 years now. I started thanks to game development, and it's a passion of mine, a hobby of mine, and a lot of these things are very applicable to that field. I have over 6 years of experience at Bloomberg. I'm currently teaching modern C++ as a contractor this year. And I co-authored this book, Embracing Modern C++ Safely, with John Lakos, Rostislav Plebnikov, Alistar, which is here, and many other contributors, including Nina and other people that you can find at the conference. And you can stop me around the hallways to discuss and ask questions about it. I participate in ISO C++ standardization. I'm a member of the Italian national body alongside some other very experienced and talented people. And I like working open source stuff. I have many side projects, including the modernization of SFML, which is a library for multimedia applications. We're going to take a look at also some benchmarks and timings on how I improve the compile times in that library. I do game development on the side, and I work on tools and libraries. For example, this matches down thing, which is basically the unit of Markdown and JavaScript, is what I use to make the slides. And I do video tutorials, articles, and a lot of other crazy C++ stuff. What are we going to talk about? Why should we care about compilation times? We're going to take a look at how we can improve them. I'm going to use a flowchart-based approach where we build a flowchart together and basically give you something that you can use in every project to make sure you can improve build times. We're going to look at some low-hanging fruits first, sort of like global optimizations, and then how to profile compilation and deal with the bottlenecks you will find as the output of your profiler. Few remarks on modules. I have to say that this talk kind of is really avoiding modules, but I have some remarks here and there. And sorry about that. I just skipped to the end, but we're not done yet. Some benchmarks and examples from SFML, which is the library I'm working on. And in terms of the goals I want to achieve with this talk is making you understand what can negatively impact build times, provide actionable points to actually improve them, something that you can actually follow as a checklist, as a flowchart. A call to action, once you have these actionable points, I want to encourage you to contribute and improve your favorite libraries. It's quite easy if they never cared about build times before to make a sizable improvement, and it's a nice idea for a PR or for some sort of contribution. And just spark some interesting discussion and see what you think. Before we begin, some assumptions on my side. You must be somewhat familiar with C++ build model. I'm going to assume you know about header and source files, how compilation works, how linking works. You don't need to know all the details, but have a general idea of the build model. And also somewhat familiar with C++. I'm assuming you know what a declaration is, definition is, templates, overall resolution, ODR, and those sort of things. Disclaimer, this talk mostly focuses on CMake and Unix. So whatever you're going to see here is 100% applicable and has been tested on Linux machines, WSL, and MinGW, which is right now my main development environment for the open source projects I work on. If you use MSVC and other build systems, the main general concepts will apply, but some details might not be, applicable. And also, I will point out some tools and articles here and there that I don't have much experience with, but most of the talk will focus on things I've actually tried myself and have experience with. So I'm not going to cover everything, but mostly what I've experienced. There's no such thing as a stupid question, so I don't mind if you interrupt me, if you want a clarification or just heckle me or have an objection. Let's do that. I like to keep things interactive. Yes. ODR. ODR stands one definition rule. That's the question. And basically, it says that for every function or entity in C++, there must be only one definition in the final program. And it's something that seems obvious, but you can actually violate it and get into undefined behavior. And I'm going to show an example of that later. I try to be pretty, let's say, good at keeping references and measuring things. So every assertion or claim that I make has this sort of like source here that you can click on. The slides are available at this link, and you can see the origin of that claim of the measurement. So you should be able to replicate all the results and see for yourself what these improvements actually do. Okay, so why do we care about compilation times? So C++ has kind of this reputation that it's slow to compile, especially if you compare it to languages like C, or especially if you go on Twitter, it's very fun to say C++ is slow. And the idea behind zero-cost abstraction, which I think is a terrible misnomer, is that with the right build settings and with optimizations enabled, they can provide a zero-cost abstraction at runtime. But usually they can also have a large build time cost, or even in debug mode, they can be slower than not having the abstraction in the first place. So these are some things that make C++ a bit problematic in keeping compilation times down. And they do matter, in my opinion. We could do the math and say time is money. We take the average salary of a programmer and the average amount of hours you work and blah, blah, blah. We can figure out how much the loss is, but I'm not really interested in that. What I'm mostly interested in is also, CI time and power usage. If you have a huge CI suite with like 40 jobs and you keep recompiling over and over again, you might be wasting a lot of time and power usage because you never optimize compilation times. But also for personal experience, motivation and experimentation, iteration times are important. And honestly, I feel pretty unmotivated if I have to wait 5 minutes every time I want to make a small change to a project. So just as a show of hands, has anybody ever felt frustrated by slow build times? Okay, so there's nobody in the room that didn't raise their hand. Maybe anybody who didn't raise their hand? Okay, it's a pretty safe opinion to have. Good. And yeah, I also feel like if you have short iteration times, you try more things, and that leads to better products and an experience in terms of development. Even on modern hardware, build times can get out of hand pretty easily. So there are some sources for these claims, but basically if you try a full rebuild of Chromium, even on a very strong setup designed to build stuff, it can take up to 50 minutes. GCC, 90 minutes. Again, you can check the machines and the claims in the sources. LLVM a bit better, but still 30 minutes. And is also a barrier of entry to contributions. Like I want to work on LLVM, create a PR, but if I have to work on my laptop on the train and download LLVM and compile it, it's going to take 2 hours, right? I'm not going to contribute to it if it's so difficult to build the whole suite. And if you never care about build times for your own libraries or projects, you'd be surprised that you can often improve them significantly without much effort. And this is what I'm going to show you. There are a lot of low-hanging fruits that you can actually work on and have a noticeable impact. If you've tried to optimize it before, there's also some other things we're going to cover in the second part, which hopefully will let you squeeze a little bit extra build speed out of your projects. Okay, why can compilation times be poor in C++? So the main culprit, or one of the main culprits, is the fact that the way we deal with dependencies and inclusions is pretty archaic. It's basically copy-paste. When you have a hash include, I don't know, standard library algorithm header, this thing is going to expand with the preprocessor, it's going to include all the dependencies, it's going to become this huge 100K lines monster of a file, and it's going to be copy-pasted in every single translation unit, every single source file that needs algorithm. And the amount of churning that the compiler has to do to go through those lines is going to impact, obviously, the build time. The language itself also is a culprit. It's quite complicated if you compare to something like C. We have overall resolution, templates, template instantiation, stuff like Spine, which for people that don't know are like metaprogramming tricks to enable or disable some functions depending on some compile time predicates. And all these things also add to the complexity of compiler machinery and end up impacting compile times. If you ever use highly generic and abstracted libraries, stuff from Boost or even the standard library itself, they can tend to feel heavyweight, bulky. And there are many reasons to this. They try to be as flexible as possible. They try to be as backwards compatible as possible. And generally speaking, the people working on them don't really see build time as a priority, especially when compared against adding new features or fixing bugs, right? So there are a lot of reasons why these very useful and very important libraries might not prioritize compile speeds. In terms of what you can do in your projects, you might also have poor physical design. This is something that John Lagos talks about a lot. And the idea, is don't hash include something if a forward declaration is enough. Or try to split your program into smaller components and have clear dependencies between them. Even, beginners sometimes think, oh, templates go in header files. That's not really the rule. The rule is that the body of the template must be visible at the place where you want to instantiate it. Sometimes you can put templates in source files and avoid that sort of extra bulkiness in the header file. So this is what I talk about with physical design, that the organization of code in files, headers, and sources. And As I mentioned, for low-level libraries that you might want to use as a fundamental part of your projects, for example, unit testing libraries or container libraries, compilation times are often not a priority. There is this sort of culture that we care about compile time safety, we care about runtime performance at the expense of compilation time. But what I'm trying to show you, and hopefully I will change your mind, is that you can have everything, right? You can have good runtime performance, good safety, and also good compilation times. You just have to care about it and take some steps to improve that. So what about modules? I'm sure everybody's thinking about this. And in short, they will help, but we're not really there yet. What do I mean by that? Compiler support is still limited. I'm going to show you some things at the end of the talk if there's time, but plenty of open bugs. Some compilers don't have conforming implementations yet. Libraries and projects need to migrate. It's not like you can just turn modules on as a flag. You also have to re-architecture your library and change all your headers and source files to conform to the module. So it might be an effort that not everybody can do and might be low on the priority list for some projects. There are promising compilation time speedups. For example, there's some tweets by the author of Format Library that shows 4 times or 5 times in compile time performance improvement just by switching to modules with the standard library. So they work. And they're being actively worked on. For example, Bloomberg is sponsoring Kitware to implement and module support in CMake, and there's already some working implementation you can play around, even on Compiler Explorer. I will show you later. And yeah, as I mentioned, I want to focus on things you have control over today. But if we have time at the end of the talk, I'm going to talk a bit more in depth about modules and show you some actual examples. Okay, so at the beginning of the talk, I mentioned the flowchart. And this is what I came up with, is the steps that you want to take to improve the compilation time of any project, any library. We're going to start here. We're going to look at some low-hanging fruits. We're going to make some changes. Is it fast enough? No. We're going to start profiling compilation, and we're going to enter this loop of profile and find the bottleneck. And in terms of bottlenecks identified, it can be that you have a first-party header in your project, which is very heavyweight, a third-party header or a standard library header, and these are something that you can, there are some techniques you can use to remove these bottlenecks. If you work on Windows, you might have had the pain or pleasure working with Windows.h. Yeah, there are some interesting things you can do here. Wrapping header is the common one, but there's also modular approaches. I'm going to show you some open source libraries that you can use instead of Windows.h. And then we're going to dive into the more nitty-gritty details. If you work with templates, have you ever used Extern template, anybody? Extern templates. Okay, so just a few people. But basically, there are some features in the language that can help you control where instantiation happens and where you don't want it to happen. They sort of work sometimes. I'm going to show you some examples of that. And even metaprogramming, you can do it in many different ways. And I'm going to show you some examples from Odin Holmes about techniques that are really arcane but can speed up metaprogramming a lot. Okay, let's begin from the first step. This is the smallest flowchart, the easiest one. And it's still interesting, right? Because if you start and you ask yourself, hey, is my build time fast enough? How do you really answer that? What is fast enough? You have to decide for yourself, right? It's pretty subjective. I would say in terms of possible metrics that you can use to help you understand whether it's fast enough or not is some sort of time cost analysis, include CI time, development time, and think about, can I really afford to spend 90 minutes compiling GCC every time I want to build it from scratch? I'm not picking on GCC. Okay, I'm picking on GCC, but I could pick on any other project. Frustration and motivation is very subjective, but again, you will feel it. Like if you really feel like, oh, I don't want to go through the compilation process, maybe it is not fast enough, right? And one important point that I think matters, especially nowadays with this sort of like resurgence of interest in compilation times, especially in the game development sort of field, is reputation and marketing. If you market your library, if you market your project as something that is fast to compile, fast to include, people are going to want to use it more compared to other libraries. So it's a way you can sort of like distinguish your libraries, your products from the rest. Okay, so let's start talking about something a bit more meaningful, low-hanging fruits. What do I mean by that? I mean that these are techniques that are sort of coarse-grained and global. They affect the entire project. They're not really fine-grained. They are generally easy to introduce, and despite being easy to introduce, their impact can be quite significant. And we're going to go through those and see some example measurements of how they can affect your build times. Okay, the first one, which you probably have done before, is changing the build system. What do I mean by this? If you think about it, CMake is a build generator. You give it some sort of description of your project, and it spits out some files that then a build system will consume. By default, usually the build system is make, but you can change it to something else. The example I'm going to talk about today is Ninja, which is kind of like a drop-in alternative to make. It uses a different format, but it does the same things that make does. And it has superior scheduling algorithms. It was developed with performance in mind, better dependency tracking. It was something like a build log that is basically filled by the compilation step. More robust file change detection. It actually has multi-threaded time modification checks on Windows because the API was so bad on Windows that it was the bottleneck. So it has a lot of care put into it to be fast. It's available on all major platforms, and enabling it in CMake is trivial. What do? You just do this. You do CMake-G Ninja. G means generate for Ninja. And now CMake is going to spit out Ninja build files. Instead of using make-J or something like that, you just invoke Ninja. And by default, it will use all of your available cores. So also it has the right defaults in this sense to be as performant as possible. And then it will just build the objects just like before, produce your final executable. And I've also noticed that, especially on Windows machines and laptops, it tends to keep the system responsive. If you use make, I find everything becomes very sluggish. And if I want to kill make, it's easier to just reboot the machine sometimes. It's just a pain. But Ninja is very clean in that sense. It's easy to kill and keeps the machine responsive. Okay, why is it named Ninja? Because it's quiet and strikes quickly. Why is it quiet? It doesn't spit out millions of lines in the console by default, and it's fast. That's the idea behind the name. It was originally created for Chrome inside Google. So somebody working on the Chrome team was fed up by the build speed with make, just like, okay, I'm gonna fix it and change and create a new one. Then he made Ninja, and then I guess his life started revolving around Ninja. So, and then this was open source, and it was a huge contribution for C++ developers. Here's an example metric from Chrome. New op build, where basically all the targets are already up to date. With make took 10 seconds. With Ninja, less than 1 second. So you can see there were around 9 seconds of overhead purely because of the build system choice, which is quite a lot, especially if you build it over and over again. Here's another nice graph I got on this article by David. I'm not gonna even attempt pronouncing his surname, which is about benchmarking Ninja. And you can see that for a fresh build where where everything needs to be rebuilt, they're quite similar. Ninja has a little bit of advantage in most cases, but it really doesn't matter. But if most of your files are already in a good state, they don't need to be rebuilt, then you can see a huge gap between Make and Ninja. So there is much less overhead for figuring out dependencies, figuring out what needs to be rebuilt. And here you can see with like 100,000 source files, we are comparing 73 seconds with 1.5 seconds. So it's a huge gap in terms of performance. Okay, so I mentioned this at the beginning. I'm working on modernizing SFML. It's one of the libraries I used in my childhood that sort of introduced me to C++. And if you don't know about it, it's fairly common for beginners. It's a very easy library to create windows, put some sprites, some audio, some music, some networking. So great for smaller gaming projects or just for graphical projects. And it can be a great introduction to C++. Some universities actually use it in their C++ introductory courses as a way to make them more interactive, more fun. It's a fairly small project, around 225 source files. And one of the things I want to do with this library, other than modernizing it and bringing it to modern C++, is making it faster to compile. I want to be able to advertise to people, this is not only simple and fast at runtime, but also including it and using it doesn't affect your compile times much. So I've been working on some benchmarking and ideas on how to make this faster. This is my system. It's a pretty decent system, I believe, for maybe a few years ago. But I do have a strong processor, a lot of RAM, and an NVMe drive. And as I mentioned before, my environment of choice is MinGW on Windows. I've also been using this tool called Hyperfine. It's a great tool. Basically, it's a command line tool where you specify a command and it provides a benchmark for you, and it gives you a nice sort of mean and provides multiple runs and so on. I'm going to show an example output. So these are the results I had when building the entirety of CMake, the entirety of SFML, including examples and tests with Clang, Ccache, which we're going to talk about later, and on the top benchmark, I use Make. On the bottom one, I use Ninja. And this was a full rebuild. And as you can see here, having most of the files cached, the time with Make was around 6 seconds. The time with Ninja was less than 1 second. So if the targets are already built, they are clean, there's nothing to do, just using Make adds 6 seconds overhead for no reason. So this is something you can actually change immediately and have a significant benefit by using Ninja instead of Make. And this is the output of Hyperfine, by the way. It does multiple runs, calculates the time, and the range is a very nice tool. So I suggest using that if you ever want to benchmark something like this. Okay, second low-hanging fruit, the linker. So the default linker on most platforms is very slow, LD usually. Gold, which is an improvement over LD, is also very slow when compared to something like LLD, which is the LLVM linker. Why? There are many reasons, but I have an article here that I read, very interesting, and it talks about the fact that LLD is designed with parallelism and threading in mind. It uses custom allocators and better data structure choices. So you can read that if you want to know more technical details. Here's a performance comparison straight from the LLVM page. And as you can see here, for example, for a Chromium debug build, using LD, we get 209 seconds of just linking. So this is just linking, not building. With LLD, we get 16 seconds. So it's quite a huge gap. For smaller projects, for example, FFmpeg, LD takes around 1 second, and LLD takes less than 0.4 seconds. So there are a lot of gains to be made by changing your linker. And again, like Ninja, it's trivial to do, so there's no reason not to do it. Yeah, absolutely. Yes, I will talk about mold. Yes, so as I mentioned, it's trivial to change it. So you say gninja for Ninja, and then you simply pass -fuse LD LDD to your compiler. There are other ways you can do this. There are some linker flags in CMake that you can change, but I found that this is the most reliable way. The compiler just takes care of passing over to LLD, and it just works. The LLVM page also suggests to replace the system linker by creating an alias, because LLD is a drop-in replacement, so you can also do that if you want to globally change your linker. So how does this fare on SFML? Full Unity rebuild, we're going to talk about Unity later. With Clang, it gives me roughly a 20% speed up, 3 seconds, just by changing the linker. So as you can see, 3 seconds for basically free. It's a nice sort of improvement with minimal effort. However, even LLD is slow when you compare it to mold. What is mold? So mold is a new linker that is fairly recent. I think it's maybe 1 year ago or 2 years ago. Anyway, fairly new linker. And it's made by this guy, Rui, who is the same person who actually began the development of LLD. So somebody experienced with linkers. And it's extremely fast because it has even higher parallelization. It was designed from scratch with the idea of modern hardware, a lot of cores, a lot of wave to parallelize stuff, and even better choices of algorithm data structures. There is a very interesting in-depth comparison about the implementation techniques in this link over here. I suggest you read that if you are interested in this stuff. How does it compare? Okay, we have Chrome. New Gold takes 53 seconds, LLD takes 11.7, Mold takes 2 seconds. So it's an insane achievement, it's an incredible achievement, and this is pretty much a linker that you can forget about. It's just gonna do something, you don't even notice it. It is super fast. What are the caveats? So Mold only targets Unix-like platforms right now under the AGPL license. This is the open source version of the linker. And it should be a drop-in replacement for Gold, LLD, or whatever on those platforms. It should just work out of the box, but it's still fairly new, and I've seen a few bug reports here and there. Biggest caveat is probably this one. There are two products. There's Mold, which is open source for Unix platforms, and then there's Sold. Sold is a commercial version of Mold. I appreciate the naming scheme. Sold supports macOS, so if you want to use it for your Mac projects, you have to purchase a license, and will support Windows. So Windows support is not there yet, but it's being worked on, but it will only be added to Sold, not Mold. So that's one of the choices you have to make. The licensing is paid on a per user, per month, or year basis. You can check the pricing. I think is fairly reasonable and fair, especially for such a big improvement. So something you can consider if you want to support the project or just use the Mold version on your Unix platforms. Okay. Any questions so far? Compilation caches. This is another thing that you can enable globally. And the idea is basically, why would I ever recompile a source file if I'm always using the same compiler, the same flags, and the file hasn't changed? And when I say this, I also mean in between new fresh builds or even complete separate builds. So what a cache is in this situation, basically it's going to map the tuple of compiler, the flags, and the file hash into the output object. And this cache, you can enable it on a system level. So if you build stuff multiple times on the same system or even remotely, you can keep using the same results as long as you don't change your compiler flags or the files that you're building. Common one that I've used is Ccache, super easy to integrate. I'm going to show you that as well in a slide or two. But there's also other caches you can use. sccache is from Mozilla and is designed with cloud storage in mind. And there's also some other products which I've heard good things about, but I never used them personally, FastBuild and IncrediBuild. This is a nice diagram I got from this article, the C++ Developer's Guide to Avoiding Office Sword Fights. I'm sure a few of you will get that reference, and I suggest reading it. It's a very good article. And it basically shows very clearly how this works. If I use G++ to compile this foo file with these flags, my Ccache process here is going to figure out a hash of the file, and it's going to also hash the identity and flags of the compiler. It's going to pre-process the source file through the C++ preprocessor, and then basically before compiling the file, it's going to check, have I already compiled this before ever on this system? And if it did, then it just gives you back the object file. No need to do any compilation. Otherwise, it will compile and cache it. So it's basically just a simple caching system. And this is a benchmark of Ccache compiling itself. And basically, as you can see here, if you have, the first time it's going to take 0.7 seconds to compile the source file, and the second time is pretty much non-measurable. It's just going to immediately jump to the object file and tell you, hey, you compiled this before, here it is. So it's a very nice way of avoiding recompilation. There are some different modes that you can use Ccache in. You can force it to preprocess the file. You can force it to not preprocess the file, or only hybrid modes. But usually it doesn't really matter. The default just works fine. You can tweak this in a lot of ways, but I've noticed that it's just another thing that you should always enable. There's no reason not to have it. So how do you enable it? Here's an example of how to do that in CMake. You can put this at the beginning of your top-level CMake list txt file. You use find program. CMake has support for Ccache, so it will figure out how to find it. And if it finds the Ccache executable anywhere in path, it will basically set this variable to something which is not null. And then you can check if you actually found Ccache, and if you did, in this case I just print because I like having some more information. But then the most important thing is this set property call, and you set this global property of rule launch compile Ccache program. What does it mean? Basically, it's going to tell the CMake build generator that to prepend Ccache to every compiler invocation. So Ccache works like this. You say Ccache G++ something, and this is going to basically enable Ccache for every compiler invocation. Yes, so this is significant. If I'm rebuilding SFML and most of the files have been unchanged and I'm using the same flags and the same compiler, I get roughly a 35-50 times speed up. So it becomes pretty much instantaneous on my machine. And I found this very useful if I have multiple build folders that I'm working on in parallel. Maybe I'm trying out different branches and figuring out what I want to do. I don't have to waste time. The cache is on the system, and it doesn't matter if I have multiple build files or multiple folders, it's still going to be present, and I can rebuild stuff for basically free. It's very, very handy. And again, super easy to enable, so no reason to not do that. Some other cool things about Zcash, it supports HTTP and Redis as backends out of the box. So you could theoretically have your Redis server that acts as the cache and share the cache object file between multiple computers, very easy. And it also has explicit support for precompiled headers. So we're going to talk about that later, but there are some considerations you have to make when using Zcash with those. But there is a clear support, so you can combine the two techniques to have even stronger results. Okay, build machine configuration. You can also tweak the machine itself, right? These are platform-specific tips that I'm not going to go over, but basically for Linux, there's the Arch Linux wiki page, which has the best information for any distribution. And there are a lot of tweaks you can make to the scheduler, to the I/O system, to the swappiness of the system, and all these things. If you tweak them in a certain way, you can actually see a benefit of that. For Windows, there are a lot of things that you can find under the umbrella of gaming optimization. So if you go on Google or Reddit and look for stuff like that, you will find some tools, for example, to disable telemetry, disable Cortana, speed up the search and stuff like that. And by enabling all these things, you can get a little bit better performance on average, even when compiling stuff. But if you're building locally on Windows, like I've been doing in the past few years, I have one easy trick to boost your compilation times by 10%. This. Add an exclusion to Microsoft Defender. And it's very weird, but basically the real-time protection system in Microsoft Defender, when you are building, it will start analyzing every build artifact while you're building it. And if you open the task manager and you look at the CPU usage, in my case, it reached up to 20% CPU usage just to check the Defender. You can figure out what directories to exclude by using procmon, and you can basically check what Defender is doing and do this at your own risk, but it does make a difference in compilation times. Yes?
I would add to this that...
yeah, we have a microphone. Yeah. Thank you.
I would add to this that this only applies to other compilers. So for MSVC, they're automatically added to Windows Defender as exceptions, both CL.exe and link.exe. So if they're installed in the default location and default configuration, they're automatically added to the exception list.
Okay, thank you for the information. So I don't need to repeat because the microphone caught it. And in my environment, I was using MinGW and MSys2, so that's probably why I saw this sort of slowdown. But again, if you're using maybe WSL as well, might be another culprit. So something to keep in mind if you see weird CPU usage. And in general, take a look at your processes during compilation. You might see something that you don't expect, and it might be another way of getting an easy win out of your build times. Hardware. Yeah, this is for completeness, but yeah, you can always throw more hardware with. That's what they all say. However, I find it interesting to think about what hardware should you purchase. And I've done some research here, and there are not that many YouTube channels or websites that do benchmarking for compilation, but there are quite a few. For example, Phoronix does CPU compilation benchmarks on major projects like the Godot game engine, LLVM, or Linux, and it can give you an idea what CPU to purchase if you want the best performance there. There are some here on Tech Power Up or on YouTube, and there are also some NVMe drive benchmarks as well. And usually CPU plus drive dominate the sort of like performance of your build hardware, and RAM also matters, but a bit less. So if you want to, if you have some money to spend, you want to have a nice build machine, you should look at these sort of benchmarks. Precompiled headers. This is also a very effective technique. It requires a bit more work, but it can make huge difference as well. So let's start talking about the problem. Let's say you have this header, x.hpp. This header includes other headers. It has some preprocessor macros, some templates, whatever. And then you have a lot of source files that include this header x.hpp. What happens? Every time you include this header, since the source files are processed in parallel individually in separate translation units, the compiler has to pre-process the header, tokenize it, parse it every single time for every source file. Because again, we have an isolated build system, build model in C++ where every translation unit is its own separate thing. This work is wasteful. And if you know that you're going to reuse this header over and over again in multiple source files, the idea is why not do all this work once at the beginning, preprocess X, tokenize it and parse it, have some sort of better intermediate representation of the header, and then simply include that intermediate representation in every TU that needs it, rather than doing all the work again. And this is the concept behind precompiled headers. We can ask compilers to preprocess, this is an unfortunate choice of words, preprocess not as in calling just a preprocessor, but also tokenizing and parsing. So do some work on these headers, and then the compilers will translate these headers to some intermediate representation, which is compiler dependent. And then that IR, that intermediate representation, is going to be prepended to every source file automatically without having to do the same work on the header over and over again. And time savings can be massive. So for example, when I enable this in SFML, I have the PRs here if you want to see the changes. The baseline measurement for a full rebuild without any sort of unity or linker tricks or stuff like that was around 34 seconds. By simply enabling PCH without reuse, I'm going to talk about reuse in a second, I had 5 main targets with 5 precompiled headers, and it got down to 28.7 seconds. And then if I enable reuse, which basically means that all the targets in CMake share the same PCH, I got it down to 19 seconds. So as you can see, it's more than 10 seconds speed up from the baseline with this technique, and it's not that hard to implement. What does it mean to reuse? And basically, by default, if you just enable precompiled headers for every target in your CMake, CMake list.txt, then every target is going to rebuild its own PCH from scratch. With reuse, you can select one target that is like the base, build PCH for that, and then the other targets just reuse it from there. So you avoid recompiling the PCH over and over again. It requires a little bit of extra work to set it up, but it's usually worth it. So how does it work? This is the simplest possible way you can enable them. You create a pch.hpp file with some commonly used includes. I'm going to show an example of what you can put in there in the next slide. And then in CMake, you use target precompiled headers. You specify the name of your target here. And then you privately put in pch.hpp as a dependency. And now when CMake is going to generate your build files, it's going to instruct compilers before compiling this target, first precompile PCH, and then automatically prepend PCH to every translation unit you're going to build for that target. That's the idea there. If you want to do reuse, which basically means there's going to be one PCH and every target is going to use that same PCH, then you can do this. You can either pick, let's say, the lowest level target in your library or application, or just create a dummy one that has a dummy source file that doesn't have anything. And you're going to do the same thing as before on that target. I'm going to call it the base target. And then for every other target that you want to reuse the PCH for, then you simply use this other version of the same function, target precompiled headers, where you specify the name of the other target and then reuse underscore from the base target. So this is basically saying, if I have, I don't know, my graphics library, I want to reuse the PCH from my system library, and it's going to find the same PCH and avoid recompiling it multiple times. Now, there are some caveats with reuse, and they are fairly annoying, I have to admit. Compiler flags have to perfectly match, or the PCH will be ignored. And this is literally anything. Even a simple define that might make no sense for a target because we never use it in that target, it needs to match exactly as the one you are reusing from. We also had to do some ugly acts, for example, in SFML, because some flags we were passing in on Windows debug builds were just to rename PDB files, to produce a PDB file with the right name. But again, this also counts as a difference in flag, so CMake didn't want to use the same PCH, so we had to manually rename PDB files when PCH is enabled and just pick a random name that is the same for every single target. So it's a bit annoying sometimes to get this to work, and especially if you have like these defines that are only for certain parts of your project that don't make sense in other parts of your project. And you might have to do some work around that, but it's usually worth it for the time saving, as we've seen in the previous slide. A good idea in general is to make PCH toggleable through a flag. And we have an option, for example, in SFML to do that. Right now it's false by default, but hopefully we're going to change it in the future once we get a little bit more confidence with PCH on every platform we ship. So what do we want to put in the PCH header? This is an example of something we have in SFML. It's going to be a normal header. You can have your pragma ones or your header guard, whatever you prefer. Then I would suggest putting commonly used first-party headers that you use in your library. For example, if you have a login system, an assertion header, or some sort of basic component that you use all over the place, then it's usually beneficial to put these headers in the PCH. Expensive headers, headers that take a long time to include, and I'm going to show you how to measure that in a bit, also are a good candidate for PCH. In this case, I put windows.h. This header here is a wrapper for windows.h. I'm going to also show you that later. And then, very importantly, you're going to see a lot of benefit if you put commonly used standard library or third-party headers in the PCH. So stuff like algorithm, file system, IOStream, string, vector. These are probably used in most source files of your project. So putting them in PCH can actually give you huge time savings, preventing all the pre-processing for these headers over and over again. When to use precompiled headers? So they scale well if you have a lot of source files and frequently used expensive headers. Remember that any change you make to this file, so any change you make to the PCH HPP requires a full recompilation of the whole project. So you should limit changing that file and avoid putting in headers that might themselves change. That's why I said put in third-party stuff, standard library stuff, or headers of your project that you rarely touch. And if your PCH becomes too large, you have a lot of headers, and most source files just use a subset of those, then it might actually be detrimental, right? You don't want to have the PCH be huge, because otherwise you're going to still include this thing in every source file. So there has to be a balance between what you put in the PCH and how many times you use it. How do you determine what headers are used frequently? Honestly, like the simple grep, sort, and WC work really well for me. Just counting, hey, how many times I'm including algorithm in my project? How many times I'm including string in my project, and so on. Is a pretty good approximation. But there's also tools like include what you use, which works on with Clang, that have good CMake integration. And you can also use Clang Build Analyzer. I'm going to spend quite a bit of time on this during the talk, and we're going to cover how to use that to determine what headers are expensive and how to detect bottlenecks in your compilation process. Now, one of the things you will encounter is if you use PCH, sometimes you can use stuff like vector or map without including vector or map in your source files. And the reason is that the PCH preprocessed sort of IR is included on every source file. So you get those symbols for free. But this is not a good idea. If you want to keep good header hygiene, do not remove existing headers from source files. Don't rely on PCH being there for correctness. And having hash include vector in your source file is going to be free if you have the PCH anyway. It's not going to do a double include. And I also suggest building with PCH disabled from time to time, or at least have a CI job that does that for you, to catch these sort of issues that only happen when you accidentally start relying on PCH. Okay, any questions about precompiled headers? Yes. I'm going to repeat the question. Okay, you can.
Can you have multiple precompiled headers?
The way that it works with CMake is that if you want, you can have a precompiled header per target. So for every target, you have a different PCH. Obviously, the drawback of that is that every target needs to recompile the PCH and include every source file. So I guess that makes sense only if your targets are very different between them. For example, there's a target that uses a lot of vector but no string, and a target that uses a lot of string and no vector, then it might make sense to have separate ones. But generally speaking, I feel like the best approach is having a main PCH file with the biggest heavy hitter dependencies and then reuse it as much as possible throughout the project. Your mileage might vary, but that's my experience. Okay. Unity builds. Is another technique similar to precompiled headers in the sense that it's global, takes a little bit of work to get it activated, but it can have, again, huge benefits. The idea of a Unity build is to coalesce multiple source files into fewer larger ones. So imagine the copy-paste mechanism for include, but for source files. Sounds weird, right? something like this. CMake will generate this unity_0 CXX file, and basically this will be a copy-paste amalgamation of a bunch of source files from your project. Why would you ever do this? And surprisingly, there is a large amount of benefits. So if you think about it, if you put a bunch of source files together into the same source file, literally copy-paste them, if there are headers in common with those source files, they're going to be parsed and compiled only once instead of n times. So that's one benefit. Same for templates. If you reuse the same template, I don't know, std vector, std string, over and over again, and you put these source files together, rather than instantiating the template n times, you do it only once for the whole Unity file. The linker has to work less. For example, again, for template instantiations, there's going to be less deduplication and stitching that the linker has to do because there's less translation unit. And very surprisingly, incremental builds with Unity can actually be faster than having individual translation units because the linker has to do less work. So it's kind of counterintuitive, but you can actually measure that in some situations. You're going to have generally fewer invocations of the compiler program itself and less creation object files. So if you're going to have less sort of stress on the file system and the compiler process. And I like to call this the wish.com version of LTO. You're going to put the files together. So you're going to have more optimization opportunities that you would get with link time optimization. But you don't need to link. The sources are copy-pasted in the same place. So there is visibility for the compiler of the entire sort of source there. And you can also catch ODR violations of compile time. I'm going to show you an example of that later. And also enforce header regime best practices, such as header guards or program ones during build times as well. Okay, so how do you enable this thing? Extremely easy. You just say -d CMake Unity build on. That's a default sort of like way to enabling it. And if you pass it with Ninja and LLD, as you can see here, just these 3 flags that are not the default can make huge difference in your compile times. You can also set it on a per target basis. You just say set target properties, some target Unity build on. And if you have some problematic files, I'm going to tell you why some might be problematic soon. You can also skip them with this property. And you also have some knobs to tweak and relate the utilities for this sort of Unity build system. The batch size is the most important. You basically decide how many sources are going to be amalgamated in one batch. Usually CMake has a sensible default, but you might want to change this to a number that is balanced between parallelism and including as many sources as possible. So too big, you won't have enough parallelism. Too small, you lose benefits of Unity builds. So my recommendations are, if you're starting from scratch and you have issues with your Unity builds, enable it on a file per file basis, fix any issue that might arise, and then always keep a non-Unity CI build to catch issues like missing headers or ODR violations and stuff like that. So I'm going to show you some issues and some code soon, but in terms of drawbacks, what do we lose from this technique? This is the most important one. If you think about anonymous namespaces or static functions, static objects, it is totally legal in C++ to have the same named entity, the same named function in an anonymous namespace in 2 different source files. You can have source 0 that has anonymous namespace function f, source 1 anonymous namespace function f. These 2 are going to be 2 separate functions. There are no violations and it's legal. But if you copy paste the 2 source files into the same one, now you have a conflict, right? You have 2 functions named f. So this doesn't work with Unity builds. You have to change the name of your symbols that have internal linkage, so in anonymous namespaces, to avoid clashes. And this requires some manual work from time to time. If you do something like using namespace in your source file, which is still a sin, but it's not a mortal sin like in a header file, then with Unity builds, sometimes you can cause collisions or change the meaning of existing code. You might be pulling in some source file that uses a namespace and changes the meaning of another source file that you pulled in the same chunk. So something to be aware of. Oh man, this is not what I wanted. We're gonna get there. So, okay. Preprocessor define. If you define stuff in CP files, you must remember to undefine them at the end of the source file. Usually people don't do this because it doesn't matter, right? It's a source file. So I'm going to define at the beginning, and then who cares if I undefine it? If I don't undefine it, it's not going to leak in other source files. But if they get copy pasted together, that preprocessor define might be used in the rest of the Unity build. If you do a lot of smaller changes on a single source file, you can actually slow down iteration times. You're going to end up rebuilding the whole chunk and not just a source. But it might make sense to still keep Unity builds on and just exclude that file from the build itself. And again, as I mentioned this, if you choose a poor batch size, you're going to lose parallelism, generally higher memory usage. And similarly to this issue here with the using namespace, you might also have possible behavior changes if you have, let's say, two overloads of the same function in different source files. You bring them together, and now one overload becomes a better match because of the copy pasting behavior. Very rare, but it can happen. And you can always apply this to the third-party libraries. For example, I wanted to use libsodium with a Unity build, but they used internal linkage symbols that have the same name. I asked to change them to unique names, but I said, no, I'm not willing to support Unity builds. I don't care. So sometimes you cannot just use this with third-party libraries. Arguably, the things I mark with asterisks promote good practices. So these are drawbacks, but not really, because if using Unity builds is going to stop you from doing source scope using namespace, that's good. If using Unity builds is going to force you to undefine your preprocessor macros, that's good. And if you have overload sets that have the same name but are completely unrelated, then you shouldn't have that, right? So in general, maybe using Unity builds can make your code quality a little bit better if you tweak these things and avoid these issues in the first place. Yes?
Is there a way to have the Unity builds randomize the order of the packs each time so that it helps highlight when you hit these issues?
So that's a good question. I'm not sure you can randomize it. What I know for sure that CMake by default chunks them in the order you specify them to the target, okay? So what you could do is you could randomize the list you give to the target, and then you will get the same result. Does that make sense? Okay. But it's a nice idea for a future request to CMake.
Thanks. I would also want to add to the list of possible drawbacks there is that Unity builds, if used exclusively, can mask header dependencies. And you might have headers that are transitively included and mask independence of particular translation units or reliance on proper physical model dependencies between translation units.
That's a very good point, and another reason why I would suggest always having a build job that doesn't use Unity builds just to make sure that you avoid those mistakes. Okay, in terms of speed up, full rebuild with SFML using Clang++, LLD, and Ninja, I got a 3-4 second speed up, around 30% of the full build time, just for that CMake flag. We had a PR here. I don't remember having to change anything massive, maybe just some symbol names in anonymous namespaces. But for 30% speed up for basically free, it's another worthwhile optimization. And also very weird, but we have a Clang tidy CI job, and Chris, that is a part of the SFML team, also wrote a PR to use Unity builds on the Clang tidy job, and it got 3 times as fast. We don't know why, but it did, so we're happy about it. I guess just Clang tidy just has big overhead per source, per translation unit, rather than for the constant translation unit. So this was a nice surprise. Okay, I don't have much time. I'm just going to show you one example of the clashing symbols just to give you an idea of the problem, and then I'm going to skip through the others. So this is an example. If you have source 0 CPP and source 1 CPP, and they both have a function f in an anonymous namespace, which is usually fine, if these 2 source files end up in the same Unity build chunk, the program will fail to compile because now you're going to f define twice in the same source file. It's weird because this is not something you encounter usually, but you have to fix it yourself if you want to use Unity builds. You can rename the first one to F0, second one to F1, and you solve the problem, but it sort of changes the way you think about internal linkage functions. Because before, you knew you could have name conflicts, but if you want to support Unity builds, you have to change your naming convention for these things, which is a bit annoying. Okay, There are other cases, ODR violations. We can take a look later if we have time because I'm behind. Okay. Now, let's get to the second part of the talk. We dealt with all the low-hanging fruits. It might be very well that at this point in time your build is fast enough, but what if it isn't? What if you want to squeeze more build time performance? And I must warn you, this becomes addictive. You like to get that number down and down and down as much as possible. So, of course, if you don't know how to make it faster, you want to profile. And how do you profile compilation? Nowadays, I strongly recommend using Clang Build Analyzer or Compile Score, and they are very great tools that give you very accurate information about your compilation process. So Clang Build Analyzer is a tool developed by Aras. Again, not going to even try to pronounce the surname. And what this does, it parses the output of Clang's F-time trace flag and produces a human-friendly report. And this report actually provides actionable information. I'm going to show you an example. What is F-time trace? Guess what? Aras also developed that himself and merged it into Clang. So thank you so much for all your work. And what this flag does, it produces Chrome tracing JSON files for each compiled object file. But if you use F-time report or the GCC sort of profiler information, this is not like that. This is actually useful. It tells you, hey, I spent n seconds inside this header. I spent n seconds optimizing this function. This header took n seconds to include. So it actually gives you actionable information, not the optimization step took 40 seconds, right? You don't really know how to use that. Unfortunately, there is no equivalent in GCC or MSVC, so this requires that your code base works well with Clang. Yes?
Small correction there. There is an equivalent tool for MSVC. It's called VCPerf. It's a command line tool that collects traces during compilation and linkage stages and produces ETL files that can be analyzed with Windows Performance Analyzer.
Okay. I was not aware of that. I'll be happy to take a look later.
Yeah, there's a blog post detailing usage and examples.
Okay. Thank you for that. So is it called VCPerf, you said? VCPerf, okay. So apparently there is an equivalent for MSVC. How do you use it? You need to use Clang as your compiler, and you can do that by saying CMake CXX compiler Clang++ is the easiest way. And then you want to pass F-time trace to your compiler flags. And again, easiest way is to put it next to the linker flag we just mentioned. Then you get this tool, is open source and free. You can compile it yourself. It's very simple to compile, or just get a release build. You compile everything that you want to profile as part of your project, just normally with Ninja, whatever. Once you're done compiling, you run your Clang Build Analyzer --all dot, which is the folder of the JSON artifacts, and it will produce some analysis.bin binary format file. And then you can ask it to analyze that same file and produce an output that is human readable as a TXT file. And then I usually just chain Explorer so that I can open it in VS Code and take a look at it. So what does this actually produce? Here's an example of analysis.bin being analyzed for SFML. You get a small summary of how much time was spent in parsing, how much time was spent in the backend. Then you look at, you take a look at the files that took longest to parse. It's going to give you a nice sort of information list here about every single file that and how much time it took. And also the ones that took longer to code gen. So you have like, which file is taking most front-end time, which file is taking most optimization back-end time, and stuff like that. Now, this is also very interesting. As part of the report, you are going to know which templates took the longest to instantiate. And of course, stud file system is a heavy hitter here because it uses a unique pointer of a path of list of impl, and this is instantiated 34 times through the whole program. Every instantiation is on average 20 milliseconds, and that's the biggest heavy hitter. And unique pointer itself also needs the data and impl and stuff like that. Then we have string. So as you can see here, this is after I've done a lot of optimizations in SFML, so the standard library became our bottleneck in terms of template instantiations in this case. They are also grouped as template sets, so these are like specific instantiations, but if you want to know in general how much time unique pointer took, then here basically this is telling us that 2.3 seconds of our build time was spent instantiating unique pointer. And 3.3 seconds were spent instantiating this __end, which is basically the way libs and C++ combines together type traits. If you want to see if something is no except constructible, internally, libs and C++ will do something like stud and is constructible and is no except, something like that. So this is the way they combine type traits with short circuiting. And again, this is, in my opinion, a good candidate for something that should be a compiler built-in or something like that. It also tells you specific functions that took the logness to compile. And in general, what to do with this information is not that clear. You can either take a look at the function and see if there's something weird in there, or in my opinion, it's a good idea to take a look at these functions and maybe separate them into a separate static library and then compile them individually and link them into your program if they are really the bottleneck in compilation. And also the same for function sets. For example, we've seen that a lot of internals of vector are being compiled aggressively, probably because of optimizations. It's not that big of a deal, but you can still benchmark this stuff. And now, at the end of the report is probably the most interesting part, the expensive headers. This tells you how much time you are paying for the headers that you choose to include. And of course, first in place, very proud of his achievement, is the Windows header. And throughout the whole build process of SFML, this takes 36 seconds. This timing here doesn't consider parallelism, so basically it's 26 seconds spread across multiple cores. It's not an actual 26 seconds increase. But we can see that it was included 22 times. The average is 1.2 seconds. And we can also see the places where it was included from. So this is also a nice way of figuring out, hey, maybe in some of these files, I don't need this include, or maybe I can use a for declaration or something like that. It's a great way of actually pinpointing heavy hitting errors and figuring out how to clean them up. Then we have some other stuff. And in general, this is the output you will get. And I find it really, really valuable, really useful. On Visual Studio, if you use ClankCL, which also supports ftime trace, there is a nice extension developed by Ramon here. And it uses the same principles under the hood of analyzing the output of ftime trace, and it gives you a nice sort of set of features which are very intuitive to use. For example, just by hovering over a header, compile score will tell you how much that header is costing to your build time and how many times it gets included. You also have flame graphs, include graphs, and you can profile compilation as a whole. So if you like using Visual Studio, this might be a good extension for you, and it's based on ClankCL ftime trace. Okay, so now we know how to profile things. How can we fix the bottlenecks? So if one of your bottlenecks is a first-party header, so it's your fault, how can you improve the physical design of your program to make it faster? So in general, improving physical design is a pretty big topic, and John Lagos, as I mentioned before, has done a lot of work on this. And the idea of components and levelizations are something that you can use to improve the design of your project. What do I mean by physical design? Physical refers to everything that has to do with files. Something like how many header files do I have? How do I split in header and CPP pairs, et cetera, et cetera. So the main idea behind this principle is to split your program into physically self-contained components. And a component is basically just a pair of a header file and a source, and usually they contain just one class or maybe a set of very tightly coupled classes. And usually you should also have an associated test driver. You should limit dependencies among components. You should never have cyclical physical dependencies. And there are a lot of techniques in Lagos books to deal with this. Levelization is also another concept that Lagos is promoting a lot. And basically, it says that components reside in levels due to the relative physical dependencies. The leaf components at the very bottom of your physical hierarchy are defined to be a level 1. And the rule is that components on a certain level n can only depend on lower level components. So what this forces you to do is basically build a pyramidal hierarchy of components. You cannot have cycles, you cannot have weird dependencies, sort of like chains. You have the base, and then layer, 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 and it's easier that way to figure out the dependencies between your components. The other good benefit about this is that if you ensure that your base layer is tested, then you know that the component depending on your base layer are going to depend on only tested ones. And if you keep doing this for every layer, at the top of the hierarchy, you can be confident about the correctness of this component because it depends on everything else that has been tested before. So it gives you also a little bit extra confidence in the correctness of your program. I'm not going to spend much time on this. There is a universe of things to say, but if you're interested, again, I recommend Lagos' work. He's been working with this his whole life. He's an authority on physical design. In terms of basic advice, declaration definitions, I would say always put the definition in a CPP file unless you intentionally want to inline the function. Seems basic, but sometimes people out of laziness just don't do this. So if I have a component class and I have a member function f, instead of putting the body right in the header file, I should put it in the CPP file. Why is this good? You know, the body doesn't get parsed multiple times, and potentially I can move some includes from the header to the CPP file if I need them in the implementation of f. But did you also know that you could put default in the source file like this? Anybody knew this before? Okay. So roughly half the room. Yeah, for example, you can also put equals default in the source file. So again, this can sometimes speed up compilation times and prevent tight coupling between header and source. Yes?
The default in the CPP file is not the same as the default in the header file because you will lose triviality.
Yes, so the comment from Alisdair is language lawyerish comment, which is very important. Default in the CPP file doesn't preserve triviality. And in the book that we co-authored, Embracing Modern C++ Safely, we covered this in depth. In fact, I have a shameless self-plug here. We have this section where we actually check all the differences between putting in the header file and source file and all the sort of like consequences of doing that. Forward declarations. So for first-party types, so types that you own, types that you can actually have access to, I would say prefer forward declarations rather than headers whenever you can. Why do I say first-party types? Because for third-party types that you don't really own, you have no guarantee that one day the library author decides, oh, this is not a class anymore, now it's a type alias. And then your forward declaration is going to be broken. And in general, forward declarations can be used in many more places than what you might expect. Here's an example class. It's called zoo. I have my class animal forward declaration, and then I have my public interface. I have this function that returns animal by value, and this function that takes animal by value, and a vector of animal over here. And then in my CPP, I include animal, and I can do some stuff with it. I can push back. So how many of you think this code is valid? One person. So why you think it's not valid? What's wrong with it? Alistair.
There's no include for vector.
There's no? Okay, somebody else who is not Alistair. Why do you think it's not valid? But yes, I forgot to include vector. That's true. Maybe there's a PCH, right? You don't know. But yeah, this code is not valid as it is, but not for the reason you might think. So we get this error that says stud is completely or unbounded type identity animal. And this actually comes from vector. So all of this public interface is fine. You can return animal by value. You can take it by value. It doesn't matter if you only have a forward declaration. It's totally fine. The problem comes somewhere from vector. And vector, for some reason, seems to require animal's full definition. It needs to be a complete type. But if you think about it, vector conceptually is just a dynamic buffer. So it stores some pointer to a dynamically allocated animal array. So why does it need to know the size of animal during the default constructor? Any ideas on why vectors might complain here? Yes.
Because it's a member of the class.
So?
It needs to know the size.
But so the answer is vector is a member of the class. It needs to know the size. But the size of a vector is independent from the element you store in. The size of the vector is always fixed because internally it stores a T star to some memory buffer. So why does it need to know the size of the member? It will store a pointer to animals. Like it's going to be a pointer to a dynamic array of animals. Yes. Small buffer optimization, a very interesting thought, but is only for strings, not for vectors. Yes.
The issue I see is the destructor for zoo, where it
Yes.
runs a destructor of vector, nothing to
Yes.
do with the constructor.
Exactly, exactly. So the issue here is actually about the destructor of zoo. If you don't provide the destructor of zoo explicitly, then the compiler generator 1 will be generated in the header as a defaulted destructor. The defaulted destructor in the header doesn't have information about animal. Why do we need information about the animal in the destructor? Because when we destroy animal, we obviously need to know the complete type and call its destructor. So how do you make this work? Like this. You add your constructor and destructor. Maybe you don't even need the constructor, probably not. But then you can default them in the CPP file. And just by making this small change, now this code is completely valid. And the zoo.h header does not expose animal.h at all. It's only included in zoo.cpp, and you save the dependency. And it seems weird, but this is what matters. This sort of like the structure here tells you instantiate, or rather, provide the body of the destructor at this point in time in the source file where you have information about animal, because before in the header files you don't. Question? Yeah.
So the biggest problem I see with this is that your animal is still part of your public interface, but you don't include it, so you're forcing that job onto your consumers.
Yes.
Which I suppose is the trade-off here, is that your
Yeah.
headers become awkward to use.
Yes, that's a very good point. And I'm going to cover this, but I'll just reply to it right now, right? The concern is now if I want to use zoo as a consumer, I also need to include animal as a consumer. So you providing this sort of like implicit requirement for consumers of zoo to include animals themselves. So I don't recommend doing this for public facing headers. Like if this was a component that you expose to the users of your library, you shouldn't really do this because it just makes it harder for the users to consume it. But it is an internal component in your library and you can have a fine-grained control of where you include things. This might be a good idea because you might have places where you just need the declaration of zoo and places where you actually need animal itself. So it depends on where you use this. So thank you for pointing that out, but it's an important distinction. Yes. Yes, so I'm just going to repeat that. Thank you, Alasdair. But I did miss zoo : prefix here. It's the correct syntax for the definition here is going to be zoo : zoo and zoo : tilde zoo. So thank you for catching that. Yes.
This is going to sound incredibly lazy, but are there any Clang tools or other magic that will help you find these things? Say you're including a file, but you really don't need to.
So there is include what you use that I mentioned before. I'm going to show it again in a few slides. But basically, it's a tool that is Clang-based, and it tells you, hey, this include here could be forward declaration, or this include here is completely unused. The output is pretty noisy, and it's not always accurate, so it gives you an approximation. Then you have to go and check yourself, but it's a good enough thing.
I'm sorry, I have to ask, why do you default in the class instead of just writing curly braces? I mean, you're not gaining anything because it's not trivial. Is it just?
I guess.
Prettiness?
Prettiness, yeah.
Okay.
It's bold. It's bold.
Putting it like Alistair says, it's not trivial actually. It just gives you empty.
Yeah, I mean,
braces
you could definitely put open close curly braces. It would have the same effect.
But
right?
do you see any benefit to putting default?
I haven't thought about this deeply, but I think they're equivalent in this case. I don't see any benefit. Maybe Alasdair can. Intention, probably, yeah. I would say this is guaranteed to be empty. But again, it's pretty easy to see that also empty block is empty. Yeah, that's a very fair point, actually. The comment is, if you have an empty block, there might be the chance that you meant to put something in there, but you forgot. If you put equals default, it's quite more clear that your intention was to keep it defaulted. So thank you for, yeah. No, it makes sense. It makes sense, yeah. So the comment is triviality. We mentioned this before. If you do in the source file, also triviality is never preserved. It has to be in the header file as well. So this doesn't work here. Yeah.
Don't we run into troubles with the core guidelines, which says if you implement even default, implement one of the 5 special functions that you implement all of them?
You're talking about like the rule of 5 and rule of 0. So those rules are good when you. So the question is, don't you run in trouble with the rule of 5, rule of 0? Those rules are applicable when you're building a class that actually manages a resource, right? If I'm writing my own vector, then I should follow the rule of 5. But if I'm just using a vector as a data member, I can rely on the vector following the rule of 5, and I don't need to follow the same thing for my class. So in this case, I will follow the rule of 0, which says don't implement anything. And I think this follows the rule of 0 as I'm not implementing any constructor, is doing the defaulting. Yes.
Right. The comment regarding this equals default versus curly braces, right? Does equals default still propagates things like no except and context?
So like propagates what, sorry?
No except and context.
Okay.
Right, because curly braces will just not have them. With equals default in the header file at least, those are propagated from members and other properties of the class. I don't know how is it about CPP.
Yeah, I'm not sure that applies if it's in the source because, yeah, it's not on the declaration. So Alasdair is shaking his head and...
If you think about it, if it's not in the header, the compiler can't see a different definition in the CPP file.
Yeah. So what you said is true for default in the header file, but not in the source file. Okay, gonna go forward a bit. We're halfway through the talk and I have 17 minutes. That's good. Same trick can be used for unique pointer. I find this really, really handy actually, because sometimes I've had these issues before and I've had people come to me and say, why can't I do this? And the idea is if you have some sort of subsystem which has some dependency and you want to store this dependency as a unique pointer, you should be able to forward declare dependency, right? And then have the unique pointer as a data member. But unless you provide the destructor definition in the source file, you will get a compile time error. So you have to explicitly say my destructor has to be in the source file, otherwise it will be a compile time error. And this is what we mentioned before. Only do this for non-publicly exposed headers, because otherwise you're forcing the client to include the header that you're just forward declaring. So do this internally in your library, but if your zoo, for example, is a public-facing header, just include animal. Is going to make life easier for your clients. Pimple, very common technique, I guess. Anybody doesn't know about Pimple? Few people, okay. So the idea is completely isolate the implementation of something and put it in the CP file and keep the header file as isolated as possible. How does that work? Something like this is an example from my game Open Hexagon, where I use the Steam API to perform workshop stuff and stuff like that. And it's fairly heavyweight, so I want to hide it. What do? I have my Steam Manager class here, and I have a private inner class called impl, and then I have a unique pointer to impl, and that's it. This doesn't include anything else. It just includes memory and provides the public interface and nothing else. All the interesting bits are in the source file where I actually define impl. So I will include my Steam API, which is possibly expensive, my windows.h, which as we mentioned before is expensive. And then in the impl here, I'm gonna start using those headers and those APIs. The constructor and destructor of Steam Manager will simply allocate impl as a unique pointer and store it inside a data member. And then the API functions will just forward the behavior to the impl. So what I achieve by this is that the header file is as lightweight as possible and all the external dependencies are hidden in the CP file through this indirection over here. Make sense to the people that I've never seen before? Okay. And again, if these headers are expensive, this can be a huge win. Now, of course, the drawback is I have indirection here and allocation. So don't do this for things that you want to have a lot of objects in a hot loop or something like that. Do this for subsystems that you allocate a few times and you reuse throughout your project. If you want performance and speed, then this might not be the best approach. But generally speaking, my idea that this should be the default for things that are used infrequently or outside of the hot path. This provides better encapsulation, better physical design, but don't use it if you need something to be cache friendly, invoked in a hot loop. However, use Pimple as your sort of default for bigger components. Drawbacks, so much boilerplate. Literally, you have to re-implement the same interface twice, once in the public API and once in implementation. It's very annoying. And the cost of the pointer indirection, as I mentioned, shouldn't matter. But if you want to, you can actually avoid it by using a byte buffer. I'm not going to bother with this. We have a little time. Header hygiene, do not rely on transitive inclusion, do not rely on header inclusion order, group headers together logically, and sort them by dependency level alphabetically, and include fine-grained headers, not catch-all ones. What does it mean? If you have a library that tells you, hey, my header is my library.header and includes everything, don't do that. Include library/something/something. Always include the most fine-grained thing you can find to minimize transitive includes and extra dependencies. This is an example of what I propose to do in SFML. We have our first party headers, levels 1 of SFML window, then level 2 SFML system, which is a dependency or window, then third party headers, then C++ headers, and then C library headers. And if you keep them all separate like this and alphabetically sorted, this will help you catch any sort of transitive include issue because the lower level includes come later. So there's no need that you accidentally rely on C-standard IO before anything else, and also keeps things tidy and shows you the hierarchy of inclusions right from the header file itself. This is what I was telling before. If you want to figure out if you have any unnecessary includes automatically, then there is native support in CMake for this clan-based tool called include what you use. Remember to turn off Unity builds because it's not compatible, and then you simply specify d CMake cxx include what you use with the name of the binary, which is usually what you see here. And once you do this, it's gonna tell you something like this during compilation. For example, it tells me, hey, sleep.cpp should add these lines, config.hpp for this define, and time.inline for this operator. And also, it could remove these lines. You don't need time HPP and you don't need sleep impl HPP. So it's going to give you some information about what it thinks that should be added and removed in terms of includes. It's not always accurate. For example, inl files are used for the implementation of templates. In this case, we don't want to include them. In this case, we just want to include the actual header file. But most of the times, it gives you a good enough approximation to figure out if you have some unnecessary headers that can be removed from your include directives and can be replaced with forwarding declaration. Yes.
So you include animal.h in your header file, include what you used. What's your opinion? Should you include animal.h also in your CPP file?
My opinion is it depends on whether the header publicly facing or not. If you're asking what include what you use would do, I don't know. I haven't tested it in this case. Okay. Okay, third-party headers. I'm gonna go a bit faster through this. I wanna get to Extern template at least. So generally, my recommendation here, if your bottleneck is a third-party library, which is very expensive, you can see that your expensive header report from Clan Build Analyzer points out something like this. Then, first of all, don't include it unnecessarily. Consider pimple or isolating it in a CPP file, as I've done for SQLite ORM in my game. Or consider forward declaring or checking if the library provides a forward header. Some libraries, like the standard library, they provide iOS forward and iOS stream. If you're just using the declarations, use iOS forward, and then in your source file, use iOS stream. And some libraries also do this. And if you're building a library, you should consider providing this to your clients. But the most important thing is to pick those libraries carefully. And libraries that are fast to compile are often bragging about it, which is a good thing. For example, doctest and Boost ext ut, these are two unit testing frameworks, really care about compile times, and they say it, and it's good. And for example, in this benchmark here from the Boost ut repository, you can see that compared to things like Catch, Google Test, and Boost.test, both doctest and UT have much better compilation speeds. So if you have a lot of test drivers, this can adapt over time, and you want the overhead of the testing library to be as minimal as possible. So picking a good library in this sense can make a difference. And usually, for example, doctest is very similar to Catch, so replacing one with the other is not that difficult. Yes, so if a library that you need doesn't care much about compilation times, consider complaining or not. I would probably say consider politely requesting improvements. And I would tell you, you know what's better than a request? Actually making the improvement. So I think this is an important point I want to make in this talk. If you learn something that you didn't know before about how to improve compilation speeds, consider contributing those things to another person's project and seeing if you can improve the compilation times. It's good for everybody, right? I've done this for SFML. I've done this for this Rely project, which is also another game development project. I've done something for SQLite ORM. And, you know, I'm proud of the fact that people using these libraries will benefit from those changes. And they were fairly easy to make. So why don't do this for your libraries and big things that you use? Anybody want to commit to this? No? Okay. Just remember, you're not making the world a better place. Alternatively, consider competing. This is also interesting, right? Fast to compile lightweight libraries are especially sought after nowadays, especially in game development. So if you have a very good library with very good functionality, but it's very slow to compile, make your own competitor say, hey, I can do what this library can do, but it's 10 times faster to compile, right? And it's a nice idea for a project and for something that people will end up using. Examples of this are, for example, Dear EMGUI, or whatever you want to pronounce it, IMGUI. And it's basically a library that's super lightweight, provides immediate mode graphical user interface, and it's used everywhere in game development because it's just so easy to integrate and so fast to compile. So people want these sort of things. Okay, this one is interesting. Standard library header. What if you've optimized your first-party headers, third-party headers, and now your bottleneck is a header from the standard library? You can possibly not use the standard library, right? You can. So this is a very cool website. It's called the C++ Compile Health Watchdog by Philip Pretner. And I want to be able to click on it, but I can't. So I'm just going to do this. And it's an interactive table showing you the impact of C++ standard library headers, boost headers, and stuff like that. So if I sort by impact, which is a metric that takes into account the blow to the binary size plus the compilation time, I can see that something like file system, just including it, just including file system and not doing anything with it, increases the compilation time of a source file by around 250, 350 milliseconds, just including it. So these are heavyweight headers. And just by including it, you're adding 30K lines to your source file. So it's pretty expensive. You can also see rejects and future and complex. You have this sort of ranking here. So, you know, if you're including C time and C string a lot, you shouldn't care, right? But if you find yourself including stuff like rejects and file system a lot, then those might be problematic headers for your compilation times. You can see the same for boost, you know, it takes a lot of time. So it's important to pick and choose these headers, and if they have a big impact, only use them if you actually need them. Example of this, algorithm. Algorithm is often used just for min and max, but if you simply re-implement min and max yourself and not include algorithm, you can get something like a 250 millisecond speed up per source file. I did this in FML. Initially, it was rejected because it was like, no, we don't want to maintain our min and max. But then I sneaked it in because and it worked. Other thing is like with every standard, things get added to headers. So algorithm specifically in 14, it took 0.09 seconds. In 17, 0.29 seconds. And in 20, 0.7 seconds. It was like 7 times slower than 14. And the reason is ranges, for example. They added more stuff for ranges and improved algorithms. It's good for functionality, but it keeps slowing down build times. So every time you include a standard header, you might be paying a big price. Why? Compilation speed is often not a priority for implementers. And again, I'm not digging on them. I'm just saying there are better priorities. They want to actually implement the features. They want to actually fix the bugs. And then if they have time, which they don't, they're going to optimize compilation speeds. Headers are implemented with backwards compatibility in mind. If you include algorithm from libstandard C++, this thing has to work even in 98 mode up to 23 mode. And the standard library maintainers are not going to have a single implementation for each version of the standard. They're going to have one that works for everything with if-defs and stuff like that. And sometimes it's easier to use a slower technique that works for multiple standards compared to having multiple optimizations. And it's totally fair. And in general, the way the standard library is defined and the standards specify how it should be is heavily templated, overly complicated, flexible, general purpose, but you pay some price for that. And I find this very interesting. Just open the headers yourself. Take a look at type traits, for example. Take a look at algorithm, and you're going to see a lot of stuff in there. And all of these things are open source, so you can just take a look at them and figure out why they are so slow. Physical design considerations apply here as well. As I mentioned, use forwarding headers and place heavy hitter in the PCH. Requesting improvements in this area is very difficult, as I mentioned, because of economics of work in this case. But even contributing improvements is very difficult. So one of the things I tried for libstandard C++ after measuring was trying to remove tuple from memory, because for some reason, std tuple of t star and t deleter is used as a data member of unique pointer instead of a handwritten sort of implementation. So in my PR, I changed it to a custom pair, and I have the diff here. And I thought, like, this is trivial, right? I'm just going to change the tuple to my own tuple that does EBO and everything. But then my dreams were crushed by Jonathan Wakely, which is one of the maintainers of GCC and libstandard C++. And even this small change, like replacing tuple with my own tuple that is faster to compile, would be an ABI break, because it would change the layout for a deleter that has the final specifier. Another good reason to hate final. But yeah, so basically the way tuple handles with final has a certain ABI, and if I do it in my own tuple, then it will be different. So there are a lot of very small things, especially related to ABI and backwards compatibility with things that are wrong, but the compiler implementers don't want to break, that prevent these sort of improvements from being added. And yes, competing with a standard library surprisingly often makes sense. I have 3 minutes, and we're entering undefined behavior territory. This is going to be interesting. So it is undefined behavior to add declaration to standard unless it's explicitly permitted by the C++ standard. But rules are made to be broken, right? Who cares? So if you want to forward declare standard library entities, it's actually quite hard to get the forward declaration right. Sometimes they have tape aliases, default template parameters, and so on. So some nice people that don't like rules, they broke them, and they made some libraries for you. Philip Tretton, the same person that made the Watchdog website, started this idea and made the first repo, CVP standard forward. And then this person, Hole, also made a successor fork that supports all of C++17. There's also a line talk about it. And these are open source libraries that you can use to forward declare standard library types. As an example here, the rule for send forward is that if you want to forward declare string, you include std forward /string and std forward /vector. For types that don't need default template parameters, you can simply use std string. It's going to work just fine. For types like vector, which has default template parameters like the allocator, then you have to use std forward : vector. This works on most platforms, but it's technically UB, so I cannot recommend you to do it, but it works, until it doesn't anymore. And what sort of benefit do you see with this? Basically, including this header is zero cost. They are just declarations. There's no code there. It's just the type itself. So you can save all the costs that we've seen here, like, for example, for file system, you can save up to 340 milliseconds if you use this library instead of file system and just include file system in the implementation, the source file where you use it. Undefined behavior, but if you're desperate, this is something that you can do. And finally, handwritten replacements. In certain situations, writing your replacement makes sense. One common place where I do this is unique pointer. Unique pointer is fairly easy to implement. And for example, in my game and other places where I want to save some compilation time, I just re-implement it. It's a nice exercise. And you can save up to 150 milliseconds per source file by not including memory and using your unique pointer. And there are some third-party alternatives written by people that are interested in keeping computation times down. For example, this person, Vladimir Vondrus, has this Magnum singles repository, which has single header replacements for unique pointer, optional, reference wrapper. As an example, his unique pointer implementation is around 3 times faster than memory to compile. And his reference implementation, which is the same as reference wrapper, is around 5 times faster than including functional. So these are things you can use if you need that extra speed up. Also this one over here. Okay, I'm out of time. I would like to get to other things. You are welcome to stay during the break if you want. I'm just going to conclude for the recording, and then we can talk about the other things if you want to stay. So I have some stuff on templates, metaprogramming. Here is the complete flowchart again. This is available in the slides. Again, you can use it as a way of optimizing things. And this is also a checklist that I made for the low-hanging fruits. So you can also go through this and see if you've done everything that you can to improve compilation times. So thank you for attending. These were the goals I set out at the beginning. Understand what can negatively impact build times. We did most of it. Provide actionable points. I gave you a lot of them. There's more. I hope I can give them to you during the break. And then call to action, which nobody answered to, but maybe you'll change your mind. Interesting discussion. I leave this open. We're going to be here for the conference, so you can discuss this stuff with your colleagues, with me. And some self-promotion, Embracing Modern C++ Safely. This is a book that basically covers modern C++ in details. It shows you facts, use cases, pitfalls, and annoyances. It was written by me, John Lakos, Rostislav Klebnikov, and Alistar, with the help from a lot of people from the ACCU committee, including Nina and some other very experienced people. And it's a big reference book, but for example, if you want to know everything about Extern template or everything about defaulting functions, it literally covers all the possible use cases, things that can go wrong, things that can go badly. So it's a nice reference to have. I can show you some examples later if you want. SFML, if you're looking for something to play around with graphics or make small games in C++, consider it. It's a very nice library, easy to use. And if you want to introduce newcomers to C++, it's a nice way to make it interactive and fun. Some games that I worked on, and if you want to keep in touch, this is my email, these are my contacts, and that's pretty much it. References, I have a lot of them. I even have extras for this talk, but But yeah, thank you for attending. You're welcome to stay during the break. I don't know how timing works, but we're officially over for the session. Thank you. So if you are willing, I can show you some extra stuff. I would like to show you Extern template specifically. I think it will take maximum 10 minutes. Can we do this? Yeah. Okay, so if your bottleneck is templates, so you see that in Client Build Analyzer, for example, there are a lot of instantiations that take a lot of time. One of the things you might be tempted to do is reduce those instantiations. And the way you can do that is with this C++11 feature, which is called Extern template. In the standard, it's called explicit instantiation declaration. And what it does is whenever you put this declaration as part of a translation unit, it suppresses an implicit generation for object code for a particular template specialization in that TU. I'm going to show you later. It's easier to look at it than to explain it. You must pair this feature with explicit instantiation definition, which is sort of like the opposite. You say, I want to explicitly instantiate this specialization in this TU. So here's an example. I have this header, it's called vec3util HPP, and I have this template function called cross, which performs the cross product between two three-dimensional vectors. These vectors are template classes, and this function is a template, so I have to use T everywhere, and it just, does something inside the body. Now I realize that in my project, most of the times I call cross with vectors of floats and doubles, but very rarely with other things. So instead of instantiating this cross function with float and double over and over again in every single source file where I need it, what I would like to do is say, don't instantiate it at all, and only instantiate it in some place in a source file, and then just link to those instantiations. So this is what it looks like. If I say Extern template, vec3 float, cross, etc., and same for double, with these two explicit instantiation declarations, I am saying, for any TU that includes this header, please suppress generation of these instantiations. So any TU attempting to call cross with floats or doubles will have a linker error. It will tell me, hey, I tried to find this cross function for floats and doubles, but I was never defined because we suppressed instantiation of this template. However, what I can do is in my source file, I can actually use an explicit instantiation definition just with the keyword template. And what this does, it will force generation of object code for those particular specialization in that TU. So basically what I'm saying here is don't instantiate float and doubles ever, because I want you to do that only in the source file. So what this means is if you have 100 source files where you use cross, you only have one single instantiation, which is going to be found by the linker from the object file generated from this vec3 util. Does that sort of make sense? So here's an example. I have 4 source files. They all include vec3 util HPP, so which means they get that Extern template declaration, so they do not implicitly instantiate the cross function. What happens in this case? This is what I mentioned. And if we don't link against vec3util.o, which comes from the CPP file, linking will fail. It will actually tell you, I cannot find the definition of cross for my floats and doubles. It will never be instantiated. But if we link against that source, that object file, then none of the source X files will trigger an instantiation of cross, but I will simply link against the instantiation that we forced in the CPP file. So we avoid reinstantiating this thing over and over again. What's the benefit? If we don't use Extern template, we will have 4 duplicate instantiation of cross, so extra work, and also the linker will need to deduplicate them, so that's even extra work from the linker. If we use Extern template, we will have a single instantiation in the object file over here from the source file, and the linker doesn't even have to deduplicate. So you get a huge sort of like reduction in work by both the compiler and the linker. So this is a technique you can use if you find these sort of situations. Okay, so where's the catch? In terms of general strategy, do what I showed you in the first slide. If you own a template and you know that this template is going to be used frequently with a certain T, U, or V, or whatever, then in the header for that template, provide your template definition, of course, plus Extern template declarations for all the common specializations. And then in the source, place the instantiations for those same specializations. So consumers of your library, consumers of your template, will get those things for free, and they will need to instantiate everything again and again and again. So it's a good win for the users of your library. So I love this feature. It works really well sometimes, but this is one of my experiences. In one of the games I was working on, a virtual reality mod for Quake, I was doing a lot of vector matrix operations with GLM, which is a heavily templated library for 3D graphics and mathematics. And I measured with Climb Build Analyzer that using vectors with 4 components of floats was a bottleneck. So I did this. I had my new GLM wrapper header. I included GLM, and then I had an extern template declaration for my vect4 float of struct. So basically saying, please don't instantiate vectors of 4 floats. I'm going to do this only once in the source file. Avoid these duplicate instantiations. So I did this. It compiles. It works just as before. So how much do you think my compilation time was speed up? 0. Yes. So why? This is exactly the same scenario we've seen with the cross function. And the cross function actually avoided instantiations. But here you don't. And I was kind of puzzled about this. This was before writing the book, before doing the research. So I didn't really know what I was doing. And I asked on Stack Overflow, and then Davis Herring, which is part of the ISO committee as well, and he hangs out in core evolution, so he knows what he's talking about, replied and tell me that an explicit instantiation declaration of a class template doesn't prevent implicit instantiation of the template. It merely prevents instantiating its non-inline, non-template member functions, which is often none of them. And code, which requires the class to be complete, still needs to know the layout of this class. It needs to know the data members of this class. And the only way of doing that for a template is to instantiate it, because the data members might depend on the T type of the template. So this is useless for heavily templated libraries. So in short, Extern template helps a lot with non-inline functions that are expensive to instantiate, or things like the cross-product function I showed before, but doesn't help much if the bottleneck is the instantiation of the class template itself, not its member functions. So it doesn't really help in that case. But very important, modules will help. Davis mentioned that a common implementation strategy for Extern templates and explicit instantiation with modules is to actually cache the result of parsing and instantiating that template. And therefore, modules will actually improve the situations and will make this sort of system work even if the class template instantiation itself is quite expensive. Okay. In general, I suggest playing around with this, but it's easy to get puzzle and linker errors. It's easy to not get any benefit. The syntax can be verbose and intuitive. And sometimes, like if you try to make this work on all platforms like MinGW, older MVC versions, plus Linux, plus whatever you make macOS, you're gonna have your CI. Sometimes this fails, and it's really hard to figure out why. It's a feature that I wish was simplified, but there was an attempt to simplify it back in 2019, which was shut down by the Evolution incubator group because it was simply not a priority at that time. So unfortunately, this is what we left off, but I would really like to see more work in this area and destroy this misconception that templates have to be slow in C++ to compile. We can actually do better in that area. Just the last thing, and I'm going to finish. Was it worth it in SFML? Not really. We got a minor 5% speed up in the test suite by doing Extern template for common pretty printers in our tests and stuff like that. So it's a little bit, but I don't know if it's worth the pain. And yeah, that's pretty much it. Alistair.
Worrying that there's still a few bugs around because this was one of the oldest features added to C++ 11 based upon existing experience within GCC and other compilers. So
yes.
Yeah, that surprised me. Yeah. I learned something.
Yeah, one of these bugs, for example, is MinGW specific with GCC, and it's been open since, I think, 2014. And yeah, so no, people don't really care about this feature that much, unfortunately. But it's something that I would like to see expanded in the future. Anyway, thank you for staying longer. Hope you learned something new. And thank you again. Enjoy your remaining part of the break. And if you want to talk about this and see the other side and stuff like that, just catch me around and I can show you some more stuff. Thank you.